Okay, let's begin. We're going to finish our discussion of exponentials and logarithms with the application to growth and decay problems. So this handout that I gave you last week. Yes.
Well, I wasn't here the day that you gave, so.
Was that last class? Or before that?
It was before last class.
Oh, yeah.
It was the last class before.
It was the last class before spring break. So,
Did you post it on the site for the class or not?
I don't think so. I don't remember. Maybe I'll do that. I'll post it. But yeah, I handed it out a while ago. We're gonna finish that up. So, basically to summarize, we have exponential growth. Right? I remember, we know that we undergo exponential growth if they'll tell you keywords, they'll actually mention exponential growth specifically. Or it will be a case of you have a bank account and it's compounded continuously, or they'll say something is growing proportional to its current size, or they'll tell you something is growing by some fixed percentage rate. And that yields exponential growth. And one of the equations that deal with that, one that you can almost ignore, I'm not going to test you on it, but I'll talk about it, is what's called the differential equation. And it's simply P prime equals RT. The actual equation for the quantity, P of t, is equal to P naught e to the RT, like the purge formula, call it purge formula. Third one, it talks about the actual, it's called an initial condition. So this is the amount of the quantity at time 0, which we call P naught. And the fourth one is something that talks about time to double. The time for the quantity to double is ln2 divided by r, turns out. And decay is pretty much the same. So this is when you're decreasing proportional to your current size, or you're decreasing by a fixed percentage, or you have a radioactive substance or anything like that. These are keywords. So this is called exponential decay. And the equations look pretty much the same, except your r's are replaced with negative r's. So the differential equation would be P prime equals minus RP. The actual equation for P of t would be equal to P naught e to the r minus RT. This will be the same, and there's something called the half-life, which I define as T sub h, which is ln2 over r. So that's the time taken for you to have half of what you started with. So those of you in bio or chemistry would already be used to that concept, right? So this is the time taken to have half of what you started with. And so what you need to know is what these things are. So the P is the current amount of the quantity at time t. P naught is the initial amount. R is it's called the growth constant. Right? So this is usually the percentage as a decimal. So they'll tell you a percentage at which it's growing, and if you write that as a decimal, that will actually give you the R. And of course your T is time, the units of which will usually be made clear in the question. Okay, so that's basically the idea. So these are things you should have memorized. You can kind of forget equation 1, because that's actually an equation. You won't even understand what this means without calculus, because this is not a 1, it's something that we call a prime. It represents something that means a derivative. but don't worry about that too much. So on the handout, let's go through example 1. So let P of t be the current size of a population of a colony of bacteria at time t. Right? So populations grow exponentially. Turns out the more parents you have, the more kids you have. Right? It doesn't grow in a linear fashion. So that's also a very common situation for exponential growth. At 10 a.m. there are 50 bacteria. At 3 p.m. there are 350. Assume the rate of growth of the population is proportional to its current size. There's a key phrase, which I mentioned last time. And then it gives you a list of problems, right? Now on an actual test, you'll actually be asked maybe 2 of these or 1 or 2 of these, and you would not be asked on like the differential equation, just so that we're clear. But I want to show you several situations, so whichever one shows up, you'll be able to deal with it. So here, it's called find the relative growth rate of the population. And as I showed on the first page, that's another name for R. It's also called the relative growth rate. Whenever you see relative growth rate, that's talking about R. Okay. So find the relative growth rate. So the first problem is asking you to find R. So how do you think you would go about finding R? Ideas? So we saw that key phrase, grows proportionally to its current size. So we know we're dealing with exponential growth. So immediately we know that these 4 equations are now relevant. And R actually shows up in a couple of them. Shows up here, shows up here, shows up here, but that's the situation we don't really care about either. Now, of course, in this equation, it talks about doubling time, which we don't actually know the doubling time. And so the only other equation that has R is this one. So that's probably the one I want to use. So they already know the initial amount, so that's what I'm going to actually set up. So set time equals 0 to be 10 a.m. This would mean they are measured at 2 times, 10 a.m. and 3 p.m. So let's say I'm even measuring it in hours. So this means t equals 5 represents 3 p.m. Right? So here I'm measuring t as time in hours. Okay, so how much did we have at time equals 0? They told us 50. In other words, we're given that the initial amount is 50. We're also given that the amount when time is equal to 5 is equal to 350.
3.
Come in?
At 3 p.m., right? 3? At 3, not 5.
No, time is in hours. The start is at 10 a.m. So read the question. It says 10 a.m. We're talking about from 10 a.m. to 3 p.m. Right, so the time that has elapsed is 5 hours. So now, what I would do, using P equals P naught E to the RT, I know the current value is 350 when we started with an initial value of 50. And we hit the value 350 when time is 5. So we end up with that equation right there. So now the goal is solve for R. How would you solve for R in that equation? Andy?
Start with dividing by 50.
Divide by 50. So on that side we'd get what, 7? Then
ln.
Right, you log both sides to get rid of the exponential. We spoke about that last time. So that will kill that. And so we have 5r equals ln of 7. And then what? Just now divide by 5. So r would be ln of 7 over 5. That's the answer to part A. Part B. Find the formula for P of t. Now we know that P of t is equal to P naught e to the RT. This means that P of t is equal to 50, because that's P naught, e to the ln of 7 over 5, because that's r, times t. That's the formula. C. What is the size of the population at 4 p.m.? What is size referring to here? Huh?
The amount of bacteria.
Right, so which variable in the equation is that size referring to? Is it P, P naught, R, or T? What is size referring to?
P.
The P, right? So this is the P. So this asks you for the P when T equals
4.
T is measuring the time in hours since 10 a.m.
Oh, 6?
T is 6. So all that means, we actually know what P is. Just plug in T equals 6. And that's your answer. Once you actually know how to read the problem, it's actually not so bad. The worst thing you have to do is like use a log to cancel an exponential. Yeah, and that's the answer. D. We would skip D because that's asking about the equation I told you to ignore. Because for this you use equation 1. Next semester you can come back to this handout and then you can do D. So that wouldn't really be something that's asked. E. When will the population reach 1,500? What is that asking for? Yeah?
Is it asking for time?
It's asking for time. When is time? So they want to know what is t equal to when what occurs? What needs to be 1,500?
Population.
P. So you read the problem, you want to translate it to the symbols that are in your equation. So now you can actually use the equation to answer the question. So this is saying when this guy has a value of 1,500, what is that guy? So that's the relevant equation, and I care about this part. So now I would divide both sides by 50. And so that would go into what, 30? Now I need to solve for the t, which means I need to get rid of the exponential, ln both sides. Right, use logs to kill exponentials. So this means we have ln of 30 is equal to ln of 7 over 5 t. And so this means that t would be, well, 5 ln of 30 over ln of 7. I helped you guys a lot there. Now, try to get through this one mostly on your own. Example 2. Hopefully me going through those kind of gave you an idea of how you want to use these equations. First you want to interpret the question in terms of the symbols in the equation, so know when to solve which equation, what you need to plug in, what you need to solve for. Let's look at example 2. Yeah, we're not doing the first one. So now this says the half-life of a radioactive substance is 30 years. Okay, so that's decay. So radioactive substances are known to actually decay exponentially. They decrease by a percentage value of what's remaining. The half-life of a radioactive substance is 30 years. Suppose you start out with a 200 milligram sample of the substance, and suppose you set P of t to represent the mass remaining after t years. So time is measured in years here. Find a formula for P of t. Okay, go. What would you do? So as Rosalie said, radioactive implies you're looking at exponential decay. So you know what problem set you should be, what set of equations you should be looking at. Okay, tell me how to find P of t.
Use the second formula.
Okay. What does that say?
P of t is equal to P0.
P naught? Oh, yeah. P sub 0 or P naught is how we refer to it, yeah.
E minus RT.
Raised to the minus RT, okay. So how do you actually find it? So in this, with these equations, hopefully you recognize by me calling this P of t, I'm thinking of this as a function of time, which means that t is my input, that's like my x value, and the p is like the output, that's like the y value. So the x and y, you leave them as a variable if you're finding the formula. So when someone says to find the formula P of t, what you really want to figure out is who's P naught and who is R. So how do we go about doing that?
The initial amount would be 200.
P naught equals 200. This is given. They said you start out with a 200 milligram sample. So okay, so I can plug in 200 here. I still also need to find the R. How do I go about finding the R? So there must be something in the question that tells us how to find R.
Oh,
What do we know?
it's a half-life video.
Okay, half-life is what?
30 years, so you can use the fourth formula.
So we know half-life equals 30 years. Don't really care about the units. Half-life equals 30. But we do have a formula for half-life, which is what?
So it'll be 30.
Well, what's the formula for half-life?
TH equals ln 2 over R.
ln2 over r is how we would compute half-life. Maybe I'll ask you guys why, but do you think know why at this moment? So basically them telling you the half-life is 30 is the same as them telling you ln2 over r is 30.
So you solve for R?
Right, how do you solve for r? What would r be?
Shouldn't you multiply ln to the 30 on the side?
You would do what? Yeah, Jelly?
It's ln 2 divided by 30.
ln2 over 30. So this means ultimately we can find P, which which is going to be 200 e to the minus ln 2 over 30 times t. That's the answer. How much remains after 75 years? So first figure out what is that asking me for? Huh? The question asks me how much. What is that referring to? Huh?
Quantity.
Quantity, okay, and who represents quantity? Huh? Who represents the amount of the quantity that we have? Huh? They're asking us for how much. What is how much asking for in terms of a symbol?
P.
It's asking for the P. Okay? It's asking for the P in what situation?
After
So they mentioned 75 years. What is that referring to? T. So this question, another way to phrase this, they're asking me what is P when T is 75? Now that we can translate that, it's actually pretty easy to answer. It's one step. I'm just going to go to what P is. I'm going to plug in T equals 75. Next question. After how many years will the mass be reduced to 1 milligram? So they ask us how many years. What is that referring to? T. What situation do I want to figure out T?
Would be
What is 1 milligram? P. So the amount left is 1 milligram, and I want to know what is the time when the amount is 1. So I would go back to this situation. I would plug in amount equals 1, and my goal is now to solve for time. How would I solve for time? Okay, so first divide by 200. Then what? ln both sides, get rid of the exponential. So what would T be? What would T be equal to?
30 ln 1 over 200 over ln 2, and there's a negative.
Does that make sense? Can time be negative?
No.
Is this negative? Does that make sense? That answer?
Oh no.
No?
No.
Why not?
It's already implied because it's decay.
It's already what?
Implied because it's decay. So you don't need a negative.
Yeah, but there's a negative sign here. Is this a negative number? Because we're looking for time. What do you mean a negative number of years? Is this a negative number? How do you know this answer makes sense? In other words, that's what I'm asking. How do you know if this makes sense? No idea. You know what happens when you have no idea if an answer is correct or not? Oh. And then you go, I had the answer and I erased it and put something else. Damn it. That happens when you don't know that you have the answer. You need to know when something makes sense. Why does that make sense? Because it does, that's actually the answer. But the negative sign should be troubling to you because it's talking about negative time. And we actually mentioned this last time also, by the way. So you guys need to be reviewing it. This number here is a negative number. So it's a negative times a negative, which makes it positive, right? So if you went and you did this because you feel, oh, it should be positive, now you're wrong. How do we know that that is negative?
1 over 200.
Yeah?
1 over the 200.
Yeah?
That's the negative. If you said negative 200.
So what about this makes you know it's negative?
Fraction.
Angelica?
It's equal to 200 to the negative 1.
This is that? Okay. And what does that mean?
That the whole thing is going to be negative
Because what? What does this mean? It's another way we can write this. Huh? So the negative power can come down, because that's a rule. So minus ln of 200. Now this is negative ln of 200. How do we know ln of 200 is a positive number? Well, we know that from the graph. So if my y equals ln x, what is this part here? That's 1, which means 200 is over here, which means the y value is positive. So this is a positive number, multiplied by a negative sign. That gives me a negative number, but that is equal to this. So this I know is negative, times this negative, it's positive. The answer actually makes sense. You can also look directly at ln of 1 over 200. Clearly, if this passes through 1 over 200 is actually over here. So that will give you a negative number. So there are a couple ways you could see that. Yes, it's important that you review those formulas. You need to know them like the back of your hand. You need to be able to manipulate things all the time. Anything's out of the ordinary, you can write it in a different form to know that you're correct. You don't change something when you have the right answer in the first place.
Professor?
Yeah.
How do you get rid of the 30?
I didn't get rid of the 30. This is the answer.
Okay. Well, that's a different problem.
It's the same.
Yeah.
That's the answer. So I was saying, how do you know it's the answer? Because there's a negative sign here. Well, you know that's right, because this itself is a negative number. This is why, how we know.
Okay.
Review the log rules. You need to be intimately acquainted with them. You need to be able to manipulate these symbols in your head. When you can do that, you'll never be confused. It's another common thing that causes misunderstanding. Students will be like, I really understood it, I couldn't answer at the last minute. No, then you didn't understand it. Change it because you didn't really know what you had in the first place. So that's actually the answer. E we're going to skip, that refers to the first equation. Here's another common type of problem though. So these three problem types really represent pretty much all the kinds of problems that you would see. So you're either going to have exponential growth, exponential decay. It'll usually be something talking about population for exponential growth. It'll usually be something radioactive for decay. And the other situation is you'll have a bank account compounded continuously, right? So that'll be a very specific phrase. Now, once you see the word compounded continuously, or continuous compounding, that refers to exponential growth. So seeing that phrase, you should be thinking about this. So we have a bank that pays 5% interest rate compounded continuously. And suppose you deposit $4,000 into an account with this bank. So A asks for the differential equation, so we're going to ignore that, even though it's not so hard. So in this situation, can you tell me what P is equal to?
4,000.
It's equal to 4,000?
Yeah.
And that's it, it's just 4,000? Are you guys done? That's the answer.
R is 0.05.
Okay. Where does that go? You give me your money. I tell you, I'm going to pay you 5% interest on this. You give me $4,000. You come back in 10 years and ask me, how much money do I have now? And I say, $4,000. It's going to sound okay to you. Sounds great. And you're going to be okay with that. Yes?
You have to multiply it by the interest.
So what is it going to look like?
Multiply by 0.05. So P is equal to 4,000 to the 0.05 times T.
4,000?
To the 0.05.
What do you mean to the 0.05?
Like R
Like
times.
raised as a power?
Yes. 0.05 times T.
Like that?
And E after the 4.
How do you forget the E? It's exponential growth. That means this is the formula. That will always be the formula. So if someone asks you for the amount, you should be writing something down that looks like that. you writing down 4,000 does not look like that. You have the initial amount, you have an E, and you have a power in that E. The R is going to be the interest rate written as a decimal times T. So that's actually the amount of money in the account after time T. If we were to jump to C, and I asked you, how long will it take to reach 5,000? How would you answer that question? What is this asking us for?
Time.
It says how long? It's asking for time, which is T. And what's the situation? We want to find T.
So the balance equals 5,000, so P is 5,000.
This means we want P equals 5,000.
So 5,000 equals.
So we want T when P equals 5,000. And so we can finish that up over here. So we know that P is equal to 4,000 e to the 0.05 t. So we want to put in P equals 5,000. And we want to solve for T. So that's this guy. How do we solve for that? Divide by 4,000, get 5 over 4. Then what? Then both sides. And then what? That's how. Now, of course, with your calculator, you can get the answer in a decimal, but you're not allowed to use calculators, so that's how you'd actually write your answer. You leave it like that. So, I don't know, it's just one of those days, everyone's feeling sluggish, but hopefully you guys are being quiet because you're in a quiet mood and not because you don't really understand. I mean, it's because you guys are excited about trigonometry and you want to get to the trig already. So you're like, why do we have to do this? I want to do trig. Okay, fine, let's do some trig. Like, this is what I was waiting. I don't want to talk about exponential growth. Bring on the trigonometry. Okay, let's talk about trigonometry. So we are going to cover 5.1, but 5.2. I'm kind of going to jump around between these, but by the time I get to the end of this lecture, they'll cover everything in these 3 chapters. So the first one deals with what we call the unit circle.
Oh, yes.
This one deals with, what's the title of that? Trig functions. And then this one deals with the graphs of the trig functions. But I like to cover things in a slightly different order than the textbook does it, so I'm going to cover all 3 at once in the order I want to do it. But by the time we get to the end here, we'll cover everything that your textbook would cover. But the unit circle is a good place to start because that is where trigonometry starts. So start with there, talk about the unit circle. What is the unit circle? Anyone knows? characteristic of the unit circle? Yeah? What equals to 1?
The radius?
Diameter.
The circle of radius 1. So any circle of radius 1 is the unit circle? What makes it the unit circle? Right, when someone says the unit circle, right, who are they referring to? There's a specific circle.
So the circle around the origin.
Circle centered at the origin. With radius 1. So when someone says the unit circle, that's who they're talking about, right? So it's the guy on the XY plane whose centers is 1 and centers the origin, and the radius is 1. That guy's the unit circle. What's its equation?
X squared plus y squared equals 1.
X squared plus y squared equals 1. That's the equation of the unit circle. Right? Because we looked at circles in general. It's x minus h all squared plus y minus k all squared equals r squared. So if I plug in h and k equals 0 and r equals 1, I get that equation. This equation is the equation of this object, which we call the unit circle. Now, I guess as time goes on, you're going to start to realize why it's important that we study the unit circle. But for now, let us assume it's very important for us to study this object. Right? And you'll start to see why we can study it, why we want to study the unit circle. But for now, we're going to talk about how we're going to study the unit circle. We want to know more about this circle than just the equation of the circle. How does this circle behave? How do points along this curve actually behave? That's what we want to get to. Also, I'm gonna be referring to these all the time, or eventually. So recall that what's the area of a circle of radius r? There's a formula for that. Pi r squared. Right? So that's how much space the circle takes up. For it to measure the units, we get how much space it takes up. It would be pi r squared units. What about, there's something called the circumference. Call it c. This is the distance around the edge of the circle. And c is equal to, yeah, pi r. Now we're going to be using these facts, and I'm going to assume that you know these things. Okay, so that's the unit circle. Circle centered at the origin, radius. All right. Let's start to study this guy by talking about angles in the circle. An angle, let me call it theta, take two lines that meet at a common point. A measure of the space between them is called an angle. The point where they meet, this is called the vertex of the angle. And a measure of how far these lines are apart in terms of the space in between them, we call that an angle. And we have several ways to measure this. So the units to measure angles, there is the SI unit. SI stands for the International Systems of Units, which means it's a set of units which pretty much every country in the world would understand and they'd be able to work in those units. Unless you're the United States, you want to work in feet and pounds, but most people would go with SI units. It's just a standardized unit system that pretty much everyone on the planet kind of follows most of the time. So when it comes to the SI unit for the angle, it is what we call the radian. Right? And this refers to a particular kind of angle. Which, by the way, incidentally, the Wikipedia article on the radian is actually pretty cool. So I would actually look at it. They have a lot of animations and stuff talking about it. It's really nice. Just as a side note. So here's how we think of what a radian is. Here's how we define what a radian is. So we think of the unit circle. Imagine that one of these lines is the x-axis. And what we're going to do is start at this point, and we're going to travel along the circle until we hit a distance of the radius of the circle, right? So take this distance between these 2 points, and then wrap it around the circle. Make a line hit that point, and then the angle here is what we call 1 radian. The angle that subtends an arc of the length of the radius is what we call a radian. Right? So that would be 1 radian. And then we can go to 2 radians. Right? By the time we hit here, we would have pi radians, etc. Right? So pretty much a radian cuts out a slice of the circle of r. Now the total distance around the circle is 2 pi r. So if this angle just measures along the circumference, how many radians would be in a circle? 2 pi r radians. Right, because it's literally measuring the radius around the edge of the circle. So by the time it measures all these r values going around the circle, by the time it completes it, it'll hit 2 pi because that's the circumference of the circle. So we can talk about this circle, and we can measure this point, and we can call this 0 radians if we start from here. By the time we're over here, it'll be pi radians, which is half of the distance around. And by the time it completes the journey, 0 radians will be equivalent to 2 pi radians. In the middle, you'd have pi over 2 radians. This is half the distance to pi. Over here, you'd have 1.5 pi radians. And so we can actually label the circle with the angles that we will hit. So if my theta is measured here, opening up this angle, I call that pi over 2 radians. If my theta is measured all the way over here, I call that pi radians. My theta starts here, measures all the way over here, I call that 3 pi over 2 radians. Starts here, goes all the way around, it's 2 pi radians. So this is the way we can cut up the circle. We can cut up the circle into 2 pi equal parts based on an angle that we measure as a radian. So that's called a radian. There's another way to measure angle. This is called the degree. What a degree is if we take the circle and we slice it up into 360 parts. Slice up the circle into 360 equal pizza slices, then the measure of each one of these is 1 degree. Now, we measure the radian based on the circle itself. Historically, how people came up with the degree, no one really knows. It's been a long time. But the idea was, it's probably when, back in the day when men thought of the Earth as the center of the universe, the sun was traveling around the Earth. A year is roughly 365 days. So they're kind of guessing every day the circle moves roughly 360th of the way around the Earth. So 365 was kind of weird, so they kind of rounded down. Oh, let's cut it into 360 parts. So this thing represents the solar system, you know, and the planet Earth or whatever. So this came up from very, like nothing to do mathematical. It's just like a convention that people did. Hey, it would be pretty cool if we slice this up into 360 pieces, right? And you end up with 1 degree equals the angle that makes one of these pieces. So this means a circle has 360 degrees. By the way, the notation for that is 360 with a little circle in the power here. Or equivalently, 2 pi radians. Of course, this would mean that 2 pi radians is equal to 360 degrees. Or in other words, we get the first 2 important equations. Well, all the equations so far were important. But we get the fact that we can measure 1 radian as being 180 over pi degrees. So that's one equation that we can use to convert. And we end up with 1 degree being pi over 180 radians. These 2 equations are very important. We'll actually use it in the future. So normally if you want to convert from 1 unit of measuring the angle to another unit, you can use these 2 equations. It'll be quite a few sections before your textbook introduces this, but it's kind of low-hanging fruit to actually get it now. So that's what the unit circle is, that's what an angle is, that's how they're measured. Now let's go back to the circle, and we want to actually talk about points on the circle as measured by angles. Create an angle starting at the positive x-axis and opening counterclockwise. Okay, so here we have the unit circle. Start an angle here and open counterclockwise. Some angle theta, doesn't matter what units you're talking about at the moment. What is the coordinate here, is the question. Now clearly, depending on the angle that we're opening, we'll hit a different point on that circle. So this coordinate is actually changing so we can measure it with a function. So let's invent some functions that's going to actually measure this. I'm going to have one function tracking the x value and have another function tracking the y value. These functions are called sine and cosine. Which that's funny how it came about. It's really a misnomer. Because the people who are coming up with the names, they thought the word for sine and cosine meant like something to do with a chord with a circle, but it ended up meaning the word blossom or something like that. So they're like, it's very embarrassing. But they come up with this function to measure the angles, and they say, call one sine, call the other one cosine, because they go together, they're co-partners, right? So a sine will measure one part, the cosine is going to measure the other part. We'll talk about that later, but we will call those guys. So track the x coordinate with a function called cosine. and the y coordinate with another function called sine. The output of these functions will depend on how wide I open this angle. Once you tell me how far I open the angle, then I can figure out the coordinates. So these guys, these are functions of theta. So I can set, so sine of theta I can think of as a function, right? So it's a function of theta. And this tracks the y value. Then there's another function that we call the cosine of theta, written this way. This tracks the x value. So in other words, when we have a circle, we open an angle and we want to talk about the coordinates that that angle meets the circle at. Tell me the angle theta. We will define the x coordinate to be cosine of theta. We define the y coordinate to be the sine of theta. So these values will change as we move around the circle. So I'm tracking them by functions that will change with the input. And thus were born the two functions sine and cosine. We want to really study this circle and the points along the circle in terms of angles inside the circle. The coordinates are tracked by these two functions, sine and cosine. These guys are important. So f of x equals sine x and f of x equals cosine x are important. We'll see why more a little bit later. But we'd like to know as much about them as we can. So we'd also like to know, how can we add them? How can we multiply them? How can we divide them? That sort of thing. Their products, their multiples, etc. Now, the products are going to be a little bit later, because once we start talking about the product of sine and cosine, we'll get into things like the double angle formulas, the addition formulas, etc. But the ratios are actually pretty easy to deal with. So we define some more functions to track these ratios. So we define another function called the tangent of theta to track the division of sine over cosine. We invent another function called secant. This will track the reciprocal of cosine. We invent another function called the cosecant. This tracks the reciprocal of sine. And we invent another function called the cotangent. This tracks the reciprocal of the tangent. Or in other words, it tracks the value that we get when we divide the cosine by the sine. These six are called the 6 trigonometric functions. You'll see why the word trigonometric is used pretty soon. Trig functions for short. So the 6 trigonometric functions are sine of theta, cosine of theta, tangent of theta, let's line it up, cosecant of theta, secant of theta, and cotangent of theta. So this guy tracks your y coordinate, this guy tracks your x coordinate, this guy tracks the ratio of those two. This tracks the reciprocal of that guy, this tracks the reciprocal of that guy, this tracks the reciprocal of that guy. So we know about all these ratios and we can look at them as functions in their own right. However, so now what you notice, then, we can get something pretty easy. Something that's really important just falls right into our lap. well, we know that the xy coordinates here, these obey a certain equation. They obey x squared plus y squared equals 1. But if my x is tracked by cosine and my y is tracked by sine, then immediately I can plug these in here and we can obtain a very important equation. How do the two main functions relate to each other? So we immediately get cosine squared plus sine squared equals 1. It's a very important equation. It's called the Pythagorean identity. It has several versions. For example, I can imagine if I were to take this equation and divide everyone by cosine squared, I would get 1 here, I would get tangent squared here, and I would get, well, 1 over cosine is secant. So I can come up with another version of this equation. So dividing by cosine squared of x, we get 1 plus tangent squared equals secant squared. Another important equation that you should know how these connect. If I take that equation and I divide by sine squared, we get, well, cosine squared divided by sine squared gives me cotangent squared. Sine squared divided by sine squared is 1, and 1 divided by sine squared would be cosecant squared. So we have these 3 equations. These are called the Pythagorean identities. And they fall into our lap once we define sine and cosine to track the equation, the points on this circle. So we kind of get these equations for free. Very important equations. I put them in a box because you have to remember them. We're going to use them eventually, but right now we're just introducing the characters in our story. Now let's see where the trig, why are they called trig functions? Tri usually means 3. So it is useful to inscribe right triangles in our circles. Well, why is that useful? So for example, I can have a circle and I can create a triangle. So if you tell me about a coordinate you care about, say over here, I can create a triangle by connecting that to the origin, connecting that over here, and then drawing this right down here. Right, so I can create this right triangle in a very natural way, where the height of this triangle actually gives me the current y value, while the base of this triangle will give me the current x value of the point. So it's a very natural to construct a triangle in this way. So I can just now think of this angle as being inside of a triangle where the top peak is touching the point that I care about. And we obtain a right triangle very easily here. So we know the radius is 1, and we know this height here is y, and this distance here is x. So Pythagoras' theorem actually tells us that x squared plus y squared is 1, which is why it's called the Pythagorean identity. So that's just a side note. Pythagoras' theorem also gives x squared plus y squared equals 1, which also implies that cosine squared plus sine squared equals 1, and that's why it's called Pythagorean identity. But being able to draw a triangle is super useful because now I can talk about circles by talking about triangles. And in general, especially in the beginning, we knew a lot more about triangles than we did about circles. So once I'm able to fit a triangle inside my circle, now Pythagoras' theorem becomes fair play. Now a bunch of theorems that I know about triangles, like the internal angles add up to 180, all those things come into fair play. And now I can talk about a circle in a whole new light. And so now we can talk about the trig functions in terms of these triangles, which is why we call them trig functions. So what do these triangles actually tell us about these trig functions? Here's one way in which this guy is actually super important. So imagine now I have the unit circle. One thing that's nice about a circle, so this is the x and y axis, is pretty much any random point someone picks in the entire xy plane. Like boom, talk about that point. I can take some circle centered at the origin where that's going to lie on top of that circle. Right? I can literally think of the origin as a bunch of circles spreading out. Right? So I can talk about all points in the xy plane as being on the circumference of some circle centered at the origin. So this is the unit circle. Let's actually connect the origin to that point. Of course, it's going to pass through this point. And here I can construct a triangle in that way. But now I can construct another triangle in a very natural way. I can talk about this big triangle over here. Now let's say this is a coordinate that I care about, x comma y. And let's say it's a distance r, right? It's on a circle with radius r. This is of course a circle with radius 1. This height here is the y value, which that height is given by sine of theta. Theta is this angle. This length here is given by cosine of theta. And so what do we get? Now we can apply something with triangles. By similar triangles, it turns out we can actually figure out what is the height of this new triangle I created. What would be the height of that triangle if you apply similar triangles? Because see, this triangle here is similar to that triangle there. Right? This triangle is created by cutting this one with a parallel line. So if I know the height here is sine, what would be the height here? Similar triangles tells us that side lengths are proportional. Which means, if this is 1, to get this I have to multiply that by r. So if this is sine theta, to get that, multiply by r. Similarly, this distance here will simply be r times the cosine. So immediately we get the following two equations. The y-coordinate is actually going to be r times the sine. Or let's start with the x-coordinate. The x-coordinate of this point is going to be r times cosine. The y-coordinate is going to be r times sine. Now, these equations are going to be super important in calculus too, but we don't care about them. They're just stepping stones on the way to what we actually care about, which is what I'm going to tell you now. What we really care about is talking about these trig functions. At this point, I'm able to say the cosine is equal to x divided by r. And I'm able to say that the sine is equal to y divided by r. Now let's talk about some naming conventions. If you have an angle here, this we call the opposite side. This we call the hypotenuse. This side we call the adjacent side. Right? So this side is y, that side is x, this side is the hypotenuse. In other words, what I just got is that the cosine is the x over r. The x is this guy, that's what we call the adjacent. R is this length that we call the hypotenuse. So get that the cosine of an angle would be, if I draw a circle, it will be equal to the adjacent over the hypotenuse length. Similarly, I get that the sine is going to be the y over r. So that's going to be the opposite over the hypotenuse length. Now we get something that we call, we can get something even further out of this. Now, remember, there was a guy we defined a while ago called tangent. This was the sine over the cosine. Well, if this is opposite over hypotenuse, and that is adjacent over hypotenuse, keep, change, flip, the hypotenuses will cancel. I can talk about the tangent as opposite over adjacent. This leads to a nice mnemonic. That we call affectionately SOHCAHTOH. The sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, the tangent is the opposite over the adjacent. Sine is opposite over hypotenuse, cosine is adjacent. Writing vertically is surprisingly hard. Adjacent over the hypotenuse, and tangent is the opposite over the adjacent. So now we have this mnemonic where we can quickly remember how to compute values of sine and cosine in terms of the lengths of triangles. So we go from having to measure angles, which is kind of weird, it's not something that's very intuitive, to actually measuring straight lines, which we can do with a ruler. It's a much easier problem. So being able to draw triangles inside of a circle was super useful. It gave us a very nice idea. So now we can talk about triangles in terms of in this interpretation. And let's see what we can squeeze out of that. So now we can talk about the sine and cosine of some special angles. Is there anything else I want to do before this? Let me make sure I'm not skipping anything. I want the story to flow. So what we're going to do now is we're going to create some right triangles where we have all the information about those right triangles. And so now we're going to get all the information we need to know about sine and cosine. So start with an equilateral triangle. Say it has length 1 all around. And of course all the angles must be the same measure. Knowing that the angles in a triangle, it adds up to 180, these must all be 60 degrees, or pi over 6, or pi over 3 radians. Now what we do is we can slice this guy into half, exactly. And that leads to this triangle, where this is 60, that's 30. The length here is 1, the length here will actually be a half, and then we can figure out the length here by, it's a right triangle, we can use Pythagoras' theorem. Says this guy is going to be the square root of this minus this squared minus that squared, so that's 1 minus a quarter. That is pretty much 3/4. And I can, because you know the laws of exponents, radicals can distribute, so you get radical 3 over 2. So this length here is radical 3 over 2. Now, remember, I can imagine this triangle as being on a circle of radius 1 centered at the origin, and now it becomes easy to talk about the sine and the cosine, because the sine gives us the vertical length, and the cosine gives us the horizontal length. So here I can start to talk about now, say, the sine of 60. SOHCAHTOA would tell us that the sine is the opposite divided by the hypotenuse. So I get that the sine of 60 is radical 3 over 2. I can talk about the cosine of 60. Cosine of an angle is the adjacent divided by the hypotenuse, that's half. Then I can talk about the sine of 30. So if I'm over here, the opposite side is that, the hypotenuse is that, so that's going to be a half. And I can talk about the cosine of 30, which is going to talk about the adjacent over the hypotenuse, so I get radical 3 over 2. At this point, I want you to notice that whenever the angles add up to 90 degrees, which is called a complementary angle, the sine and the cosine actually give you the same value. That's why one is sine and the other is cosine. That's where the names come from. So here I just figured out a bunch of values. We can actually figure out more by looking at another right triangle. This one is not an equilateral triangle. We can use isosceles triangle. I don't remember. It's one of those words that's it's in a blank portion of my mind. I can never remember how to spell isosceles. Okay, so this triangle is of course the guy where two sides are the same, but the other side could be something different. If that's 90 degrees, it means that these two angles need to be 45. And again, I can use Pythagoras' theorem. To figure out that this side would be radical 2. And now I can talk about the sine of 45 degrees. Well, this is opposite over hypotenuse. That's going to be 1 over radical 2, which I'm going to rationalize as radical 2 over 2 by multiplying and dividing by radical 2. Of course, sine and cosine are complementary. Since 45 plus 45 gives us 90, I immediately get that cosine of 45 is also radical 2 over 2. Or I can derive it from this triangle once again by taking the adjacent over the hypotenuse. Now, I know a lot of students who learn these angles by this triangle, and whenever I ask them, so what's the sine of 60? They go to their notebook and they start drawing a triangle and they try to figure it. Too long. Okay, we are going to be efficient. That's like graphing things by plotting points. Let's look at a quick way to actually know these angles.
Can we use the table?
So I'm going to give you a strategy that practice it for a day and you're going to be really good at using it, and it's going to be like someone's going to ask you what the sine of this is and you're going to just tell them, and you're like, how do you know that off the top of your head? I have to draw like a triangle. You know? Secrets, you know, work hard, you know, you got to work harder, right? But really, you know the secret. The secret is actually, it's much easier to memorize in table form. And I know some of you are going to be like, okay. This one is nice though, because there's actually a nice little trick to fill out the table. So it's kind of like a fun little game. Or at least you'll have fun when you're wowing your friends with the fact that you know sine of 30 without having to draw the triangle and they look like idiots. So I can talk about the angle here. The special ones are 30 degrees, 45 degrees, and 60 degrees. These are the angle measures in degrees. We're going to want to talk about radians all the time. So for the record, this is pi over 6 radians. This is pi over 4 radians. You can use the equation that I gave you at the very beginning to tell you how to convert these. This is pi over 3 radians. Right? But you can set it up with 30, 45, 60. These are the guys we just figured out. Now you can talk about the sine of these angles and the cosine of these angles. Okay. So pay attention. Here's how you set up the table. Count up from 1 to 3. 1, 2, 3.
3, 2, 1.
Backwards of cosine. 3, 2, 1. Take the radical, everybody. Radical of 1 is just 1. Then divide everyone by 2. And that's all the angles. So immediately I can see here, sine of 45 is radical 2 over 2, cosine of 30 is radical 3 over 2, cosine of 60 is a half, right? And the thing is, when you actually write this table out, now you'll eventually be able to visualize the table in your mind. And when someone says, oh, what's the sine of 60? Oh, 60 is all the way in the right side of the table. For the sine, I counted up from 1 to 3, radical 3 over 2, right? So you'll think of that in your head, like, how do you do that without drawing the triangle? Let me check. Wow, dude, you're so smart. No, you're not smart. Right? You just did a table. Oh, it's 1, 2, 3, 3, 2, 1. 60 is all the way on the right, so the sine would have the 3 and the cosine would have the 1, and so on and so forth. So a lot of times when I'm like doing things in class and I'm just, oh, the sine of this, cosine of that, and I'm writing down the answers, and all the students are like, how do you do that so fast? In my head, I'm seeing this the whole time, and they think I just know it. I don't know it, right? But I have a strategy that I can figure it out easily without having to worry about, what was that triangle again? Was it a 30 degrees here or 60? Was it a 1 on the leg? I don't remember. No, this I always remember. 1, 2, 3, 3, 2, 1, radical over 1, divide by 2, those are all your values. So from this you can tell all the values of sines and cosines.
You're gonna do tan?
Well, no, because if I ever need tangent of something, I just divide the two values. So if someone asks you what is tangent of 30 degrees, well, I just know that that's sine of 30 divided by cosine of 30. And then, okay, 30, that's okay. So this is going to be 1/2, and that's going to be radical 3 over 2. So I know it's 1 over radical 3. Right? So that one will take you like 2 seconds to do, and your friend will still be impressed. So it's not going to be a big deal. And this is kind of a pro tip. There's a larger table you can do, and you could add tangent to this and all sorts of stuff, but the smaller you memorize chunks, the better it is to recall, right? I know you don't think about it, but your brain actually uses fuel when you think, right? So if you have to come up with a big table in your brain, it's going to be harder than coming up with a small table in your brain. Now, if you're just relaxing and coming in, it's not going to be a big deal. But when you're under pressure and you're under stress, remembering a big table becomes significantly different from remembering a small table. So while I could populate this with even more values, I usually don't, right? So I remember this table. It turns out that all the other values, there are some other special values that I'll remember from the graphs when I tell you them, as well as if someone asks me about tangent or one of the other ones, I just divide in the way that I know. Because those equations I would already have memorized. So that's a separate memory chunk. So I just use that memory chunk as needed. I don't try to combine it into one big thing, right? Because you don't want to make a mountain over a molehill. That's a big problem that students usually have. They think of math as, oh, this one giant big thing. There's so many things to understand. No, it's a bunch of little small things that are all each individually. They're easy. Access it when you need it. So that's something called chunking, I think is actually the technical term, believe it or not.
It is.
Yeah, it's called chunking. It's a way to memorize more and actually be able to utilize information more. So it's actually, I didn't just make that up, that there's scientific evidence, whatever, to back up that if you think about things in smaller chunks, it's actually easier to recall, easier to utilize. Let's see. What can I talk about in 10 minutes? Let's talk about the fact that all students take crack.
Well, most students take calculus.
Yeah, all students take calculus. We'll go to the PC break. Okay, so, back to the circle and XY plane. Okay, so now here's something that we'll notice. Say I'm on a circle over here, and right now, let's say I'm picking points in each quadrant. By the way, these are called the, I don't know if you would know this, outside trig. But it turns out we think of the XY plane as cutting the Cartesian plane into 4 distinct parts. This part over here is called quadrant 1, and we number them increasing order going counterclockwise. So this is quadrant 2, this is quadrant 3, this is quadrant 4. Now, remember our definitions of sines and cosines. The cosine tracks the x value, the sine tracks the y value. What you'll notice about here, I'm not going to put values on these coordinates, I'm going to put the signs. Over here, both your x and y are positive. So this will give you a positive sign, this will give you a positive sign. So your sine and your cosine are positive. If you divide them, it's still positive, so the tangent is also positive. If you take the reciprocal, those are positive. So you get that all the trig functions are positive here. So that stands for all trig functions positive. So they will all output positive values. Now, do that same kind of analysis over here. A coordinate over here is going to have the x coordinate negative. So this is going to be negative. The y coordinate is positive. So remember, the x coordinate tracks the cosine. So here I get the cosine is negative, but the sine is positive. So I say, okay, I will define this as the sine being positive. Okay? So over here, this says sine, and of course, cosecant would be positive. Right? Same kind of analysis. The coordinate over here has both the x and the y are negative. So that means the cosine is negative and the sine is negative. By the way, this is a very bad habit. Don't follow me with that. Cosine and sine should never be written by themselves. They always have to act on them. Okay. So these two are negative numbers. However, if I divide a negative by a negative, I get a positive. So it turns out that the tangent is positive. So this quadrant, I know in the third quadrant, the tangent, and hence cotangent, because it's just a reciprocal of that, are positive. Everyone else is negative. Same analysis over here. My x coordinate would be positive, but my y coordinate is negative. So that tells me the cosine of whatever angle is here is positive, while the sine of that angle is going to be negative. And so the cosine is positive, so I call that C. And that stands for cosine positive. And of course, if the cosine is positive, the secant is positive because it's just 1 over cosine. So we get this ASTC, or as Rossi would say, all students take calculus. And this is just a way to remember the signs of all of these angles. The signs of the trig functions at all those angles. Right? Because no one wants to actually go coordinate by coordinate and figure out the signs. This is just a nice way to quickly remember it. Once your angle is hitting a point in the first quadrant, everyone's positive. If it hits something in the second quadrant, sign, and then you get the idea. So, all students take calculus. So it's just a buzzword of that, and this allows you to remember the signs of the trig functions in each quadrant. Which now brings up another idea. What does it mean for an angle to be in the second quadrant, or the third quadrant, or the fourth quadrant? How does that affect things? So the next natural place to talk about things would be the idea of the reference angle and the terminal angle, but we don't have time to get into that. We'll stop right there. So we'll continue the story of trigonometry next time. But we built up to all students take calculus. That's a pretty impressive feat. It's like hundreds of years of. See you guys on Monday.